Hi guys, I'm going to be doing this video just talking through the answers to the organic practice test. Hopefully it makes a good bit of sense to you. As always, if you've got any questions, just ask me. Alright, so the first question we're going through here is this one about oxaloacetate. So it asks you to draw a structural form of a polyhydroxy compound which, when oxidized with acidified potassium dichromate, produces oxaloacetate. So what you've got to identify here is some of the important bits that they're actually asking of you. So I'm just going to switch to my highlighter for a second. And what you really want to be looking at here is that they talk about the fact that it's a polyhydroxy compound, okay, and it's oxidized with acidified dichromate solution as well. So what that means is that you need to think about what polyhydroxy means, many hydroxy compounds, and what do we oxidize with acidified potassium dichromate? Well, alcohols. So the functional groups we've got up here are carboxylic acid and carboxylic acid here, which are both produced by the oxidation of a primary alcohol, and a ketone here, which is produced by the oxidation of a secondary alcohol. So all you've got to do is draw the straight carbon chain here of 4 carbons. Okay, this carboxylic acid would have come from an alcohol, same for the one down the bottom, and the ketone would have been an alcohol as well. So we've actually got butane 1,2,4 triol here is our original molecule. So just identify what the questions are asking you. Think about any time you see acidified potassium dichromate solution, it's going to be oxidation of an alcohol. Your color change is going to be orange to green when it oxidizes with a primary or secondary. State and explain whether or not you predict oxaloacetate to be soluble in water. Well, up here, you've got a very small carbon chain, so generally anything with a small carbon chain is going to be water soluble anyway. But what we've got is a polar carboxylic acid group here and here. Okay, both of those are able to form very strong hydrogen bonds with the water. It's going to be quite soluble due to that small polar chain and the polar groups that we've got. Alright, going over to page 2. Okay, so here in the next part of the question we have oxaloacetate reacting with sodium carbonate solution. So this is just an acid carbonate solution. Our carboxylic acids here are both going to react with the sodium carbonate. We're going to deprotonate the hydrogens on here to form a carboxylate salt. That's going to react with and form a bond to the sodiums plus carbon dioxide and water. So that's just a normal acid carbonate gives you salt, carbon dioxide and water reaction. The observation you're going to be seeing here is obviously effervescence of your carbon dioxide gas. Okay, and then what they're going to be doing in the next part of the question is then taking our oxaloacetate, which is a carboxylic acid, and they're going to be reacting with ethanol and heating using this apparatus here for 30 minutes with a trace of concentrated sulfuric acid. So hopefully you can see this is a reflux reaction. As soon as you see reflux and you see carboxylic acid and ethanol or an alcohol, you should think ester. So the question asks you to label the direction of water flow on the diagram. So you're going in at the bottom, out at the top always. Okay, so next page. Explain why we use a reflux apparatus. Now reflux is not just about increasing the rate of the reaction. Okay, that's the purpose of the temperature that we put in there. Reflux is actually to contain the volatile components. And what that does is that helps the reaction to react for longer. And as you know, that one of the factors that can increase your yield is time. So the longer it reacts, the more yield you're going to get. So reflux not only provides the heat, which increases the rates, but also allows it to be heated for a prolonged period of time, which increases the yield. The type of reaction is called esterification reaction, or it's a condensation reaction. You can use either of those. Draw the structural formula of the organic product of this reaction. Well, what I do for these ones is, so if I just flick back to the structure of oxaloacetate here, we know that our ester groups are going to form off of the carboxylic acid groups here. So I just put an ethanol next to each of those. Okay, and there's your ester group there with an ethanol bonded onto each one. Alright. Question 2 talks about starches. So starches are polysaccharides. That means they're complex sugars. So they're made from reacting lots and lots and lots of simple sugars together. They hold water, maintain a smooth, thick texture. Here's the structural formula. These square brackets indicate a repeating unit, and you can see the N down here indicates a repeating unit as well. So it says, draw the structural formula of the glucose monomer produced from starch. So it's just asking you within the repeating unit here to show what the individual glucose would look like. So what we've got to do is copy the exact structure here, and like a ester or an amide, this is formed via a condensation reaction. So all you've got to do is create this into a hydroxyl over here, and create this one into a hydroxyl over here. Because what happens is when these link up, water is eliminated as they add on and on and on. Okay, so they're formed by condensation reactions. So if you can just draw the stream structure, make sure you finish off your hydroxyl groups so it becomes a polyhydroxy compound, you'll be fine. It then says conversion of starch into glucose occurs by an enzyme catalyzed hydrolysis. Write 2 equations for the conversion of starch into glucose. You could really get away with this with 1 equation, and in the exam they'll probably ask you that, of just having this of starch going to glucose. Okay, the 2 equations they're looking for firstly is starch to a disaccharide like this, and then a disaccharide to a monosaccharide. Okay, but if you can just remember this starch reaction here to glucose, if you went straight down that way, you'd be fine as well. Then they're talking about the 2 different forms that you can find glucose in. So we've got glucose monomers here as a straight chain. Back here in what we drew out, this is what we call the chair structure or the ring structure. Okay, so there's 2 forms it can exist in. Here we've got an aldehyde group on the end. Okay, in the I went the wrong way, sorry. In the in the chair structure, the aldehyde group disappears as we form the bond through here. Okay, so the question asks to explain why in the straight chain form it reacts with ammoniacal silver nitrate. Ammoniacal silver nitrate is purely for reacting with aldehydes. So as soon as you see ammoniacal silver nitrate, you think Tollens test, you think silver mirror. So the straight chain form here has a aldehyde group, so it will react, whereas the chair structure before the aldehyde is gone, so there's no reaction. So let's draw the structure of the straight chain form of glucose after it has reacted with ammoniacal nitrate. Well, basically what you're doing is you're doing an oxidation, but you're doing it under alkaline conditions. Now, normally an aldehyde oxidizes to a carboxylic acid. Because it's basic, you are deprotonating your carboxylic acid group, which is why you get the carboxylate salt here. Okay, so you've got to remember, and this is about the only thing I'll ask you about Tollens reagents test apart from what you'd observe, which is a silver mirror, okay, is what the product would be, and it's the carboxylate ion. So you've got to remember and know how to do that. Then we get to a drug-related problem. So we've got paracetamol and ibuprofen, a solids at room temperature and are not very soluble in water. Circle the amide link in paracetamol. So there's the amide link between the nitrogen and the carbon. If it asks you to circle the amide group, it's this one here. Okay. If it asks you to circle the peptide group, that's the same, and an amide link is the same as a peptide link. State and explain whether paracetamol or ibuprofen is more polar by referring to the structural form of the above. Well, here in paracetamol, you've got a polar hydroxyl group here, and you've got a polar amide group. So there's 2 polar functional groups here, and you've got a non-polar aromatic benzene here. Here in ibuprofen, you've got a polar carboxylic acid group on the end here, but all of this is non-polar. So it's a much bigger non-polar section. And when you're asking or referring to a question about polarity, you must talk about polar groups and non-polar groups as well, a non-polar section. Because ibuprofen has a much bigger non-polar section and only 1 polar group, it's going to be less polar, so hence paracetamol is going to be more polar. Draw the structural formula of the 2 substances formed if paracetamol undergoes alkaline hydrolysis. Okay, well, the only functional groups that undergo alkaline hydrolysis that we're looking at are esters and amides. So what you've got to do, and I'm just going to go back to my pen for a second here, okay, is you want to have a look for where your amide link is, which is this one here. So you break that link, okay, and you draw out the 6-membered ring structure that you were looking at, okay, and that's to the NH that you had there, okay, and obviously there's the OH group over here, okay, so that's one part of it, and on the other side we've got this. Okay, so all we've done is we've broken the bond between this nitrogen and this carbon here. Okay, so that is actually a carbon, right, with, oops, sorry, no it's not. Sorry for that, completely stuffed it up. Okay, I broke that bond between that carbon double bond oxygen there, okay, to there, and then we had the nitrogen hydrogen. I'm not going to draw out the rest of it. So we just broke that bond there. All you've got to do now is make this back into the original groups that it came from, which was the amide over here. So this becomes a hydrogen. You're putting water back in because that's what hydrolysis is. And this is going back into a carboxylic acid like that, which is why down here, all right, we have the amide. Okay, and we would have the carboxylic acid here, except it actually talks about going through alkaline hydrolysis. Okay, so alkaline hydrolysis, which is here, okay, that means we're going to deprotonate our hydroxyl group here, okay, which means we have the carboxylic acid salt. So again, I've talked to you lots of times about you've got to know what happens to your amines and your carboxylic acids in acidic and alkaline conditions, and if it's an alkaline hydrolysis, you always get the carboxylate salt. Alright, moving on. Explain why ibuprofen is often mixed with sodium bicarbonate in tablet form. No equations necessary. So if you come back over here, ibuprofen, as we said, this is going to be insoluble for this massive non-polar group here. However, if you change, and I'll go back to my pen again, if you change the hydroxyl here, so this COO, oops, I'll go to actual red so you can see it. So if you change your carbon double bond oxygen OH to be the carboxylate salt like that, which is what would happen if you reacted with sodium carbonate, this is now water soluble. Okay, and so obviously it doesn't matter how big this non-polar section is, you can form ion dipole interactions with water here, and so you get a water soluble product, which is really important because your blood is majority water. Okay, and so if you get ion dipole interactions occurring between the drug, it can be absorbed into your bloodstream and transported around the body, which is really useful. Alright. Sweaty feet produce a mixture of short-chain fatty acids that smell cheesy, such as a compound with structural form is shown below. Systematic name. So what I suggest you do is you actually draw this out. Now CH32, some of you hadn't seen this before. I probably didn't need to do that, sorry. I was going to draw it, but I forgot that I actually drew it here. So draw it out. Put your carbon, carbon, COH. So this is carbon, carbon, C, double bond OH, okay? And then there's two CH3 groups there, so there and there. And if you draw it out, you can actually see this structure far more easily as 1, 2, 3, 4. So it's butanoic acid, because that's a carboxylic acid group. And then the third one is a 3-methyl group, so 3-methyl butanoic acid. Always draw them out on this scrap pieces of paper. It's always going to work out better for you. And then it says another molecule that just to smell is ethyl propanoate. So this is an ester. It's going to have a very fruity smell to it. Predict and explain whether the boiling point of ethyl propanoate will be higher or lower than the boiling point of the compound named in A. Whenever you're talking about boiling points, you always want to firstly look at molecular weight. Okay, and I did do a video on this to make sure you have a look at it. But when we talk about molecular weight, they're both going to be pretty similar. Okay, so then it comes down to polar functional groups. And ester has a polar carbon double bond O, so a carbonyl group in there. However, that can't hydrogen bond with water, whereas the carboxylic acid group here can. So if they're same molecular weight, but one of them's got ability to form stronger secondary bonds, such as hydrogen bonds, that one's going to have the high boiling point, which means ethyl propanoate here is going to be lower. Alright, so always talk about the type of secondary bonds that exist and the molecular weight. Okay, it's really important. Alkaline hydrolysis of ethyl propanoate produces ethanol and another organic compound. Identify one chemical reactor with ethyl propanoate to cause alkaline hydrolysis. We use sodium hydroxide. And draw the structural form of the other organic product formed during this reaction. We draw out ethyl propanoate. Okay, and then you work out if one part's ethanol. So I'll actually draw ethyl propanoate for you down the bottom because this is always helpful. So ethyl propanoate is going to have CH3, CH2, and sorry, it's hard to draw with the mouse. Okay, so there's your propanoate part with your 3 carbons. Okay, and then ethyl is going to be CH2, CH3. So that's ethyl propanoate. What you're doing is you are breaking in hydrolysis the carbon-oxygen bond, similar to what we did in the amide earlier. So this bit here, if I go to another colour, let's go to this bit. So this bit here is our ethanol. So what we're looking at for our other organic product is this one here, right, which is 1, 2, 3 carbons. All right, it's going to be a carboxylic acid. Okay, and now I've actually made a mistake in my answers here, because this was alkaline hydrolysis, so hopefully you've worked out that the product here should actually be the deprotonated form. So I'll see if I can get rid of this with some white. So we shouldn't actually have that in there. Okay, it's the deprotonated form, and it should be the negative. So we should get this the carboxylate salt here. So I'll adjust that on the actual answers I put up. Okay, but make sure you understand again it's alkaline hydrolysis, so we've deprotonated the carboxylic acid. Ethyl propanoate may also be hydrolyzed using water and a small amount of sulfuric acid. State why alkaline hydrolysis may be preferred as a method of hydrolysis. It's possible you will get a higher yield because you're forming the carboxylate salt. You can cause it to separate out from the ester more readily, even though propanoic acids can be reasonably water soluble. It's also probably going to be a bit safer to use some sodium hydroxide solution than a concentrated sulfuric acid, which you need to use for the reaction as well. So both of those are possible answers. Alright, a long chain carbolic acid molecules are components of triglycerides. So triglyceride is a triester of fatty acids and propan 1,2,3-triol. So state whether this triglyceride is likely to be a solid or a liquid at 25 degrees Celsius. Well, here within you've got 1, 2, 3, 4 double bonds. As soon as you introduce double bonds, your triglyceride becomes unsaturated, which makes it an oil. So it's going to be a liquid at room temperature. Systematic name of the molecule it comes from is propan 1,2,3-triol. I've talked about this. And draw the structural formula of one of the carboxylate ions produced during the alkaline hydrolysis. Well, I've just enabled each of them chains 1, 2, 3, and you can see each of the 3 different organic molecules we get here. I think these two are actually the same, so the same fatty acid. Okay, but all you do is you just copy out the chain and you just leave your carboxylate ion like that. Triglyceride shown can undergo hydrogenation if it is reacted with hydrogen. 2 reaction conditions you need a high pressure because you're using a hydrogen gas, so high pressure forces equilibrium to the right, which increases your yield. And you also need a catalyst as well. Catalyst will speed up the rate of a reaction. State whether the melting point triglyceride will increase or decrease. Well, because you're now, and I'll link these two together, because now you're actually getting rid of the double bonds, what you're now getting is all these nice straight chains like this. Okay, and so they're going to stack really nicely on top of each other like this. And what you're going to end up with is lots and lots and lots of dispersion bonds that occur between the chains. So you're going to get dispersion bonds occurring between all these chains. Because you've got a higher amount now than you had previously with the with the kinks in the chain, you're going to have a higher boiling point. So increased number of secondary bonds means an increased boiling point, which means it's now going to be a solid at room temperature. We've got a second triglyceride here. Okay, the main difference is that this one now doesn't have a double bond in this part of the triglyceride. It's got 1 here and 2 here. So this has actually got 1 less double bond than the triglyceride on the previous page, which is important because the question here asks you to determine how you could work out which one has a higher degree of unsaturation. So that means which one has the higher number of secondary bonds. So what I ask you to do is include details of apparatus use. So you're going to be using the titration here, so you need to talk about titration. The reagents you use, you're going to be using iodine. You could use bromine as well if you want. Iodine is more commonly used. And observations made, so our color changes. So we titrate both of them with iodine. Triglycerides you need to dissolve in a nonpolar solvent. Okay, even though they're both oils, I'd probably still dissolve them up in some solvent to increase the volume. And you titrate them against iodine, which is in a burette. The endpoint is determined by the first pale blue-purple color change from the iodine. If you're using bromine, it would be pale yellow to orange. If you use equal number of moles of the triglycerides, the one which requires the greater number of moles of iodine to react with has the higher degree of unsaturation. Basically, it's a 1 mole to 1 mole ratio. For every 1 mole of iodine you need, you add across 1 double bond. So the more moles of iodine you need, the more double bonds that are in there. All right. Hair is made of protein. The structure of one section of protein is here. Okay, this is cysteine, the amino acid, and they ask you to draw the structural formula. So all they're trying to work out here is if you know how to draw the structure of amino acid. Amine group on one end, carboxylic acid on the other end. So they're just asking you to complete that out. You really should be able to do that. Then it goes on to showing 2 protein chains here, joined by a sulfur-sulfur bridge. Name the type of bond that holds the 2 sulfur atoms together. It's 2 identical non-metal atoms, so it's a non-polar covalent bond. Structure of 2 protein chains in here as shown in the diagram below. Draw a hydrogen bond that forms between the 2 protein chains, indicating partial charges. So by partial charges, it means your delta plus delta negative, and a secondary hydrogen bond is shown by a dotted line. You could also, there is another spot you could put this in that I'll show. Alright, so you could have one going down there. I can't do a dotted line, sorry, at the moment because it's a small scale, but you could have one between that oxygen and that hydrogen there, and you'd obviously put delta positive here, delta negative here. Alright, so there's a couple of spots where you could do it and it wouldn't matter. State which bond is stronger, the hydrogen bond or the bond between two sulfur atoms. Hydrogen bond, and this is a question that a lot of people got wrong last year, is because they went hydrogen bonds is the strongest type of secondary bonds. Yes, correct. But a covalent bond is a primary bond, which is stronger. So the sulfur atoms bonds is a covalent bond, and that is stronger than a hydrogen bond occurring between the chains. Some alkaline hair styling products strengthen the interactions between the protein chains. Explain the effects these products have and why they are strengthened. So if you go back to the diagram, under alkaline conditions, what you're actually going to be doing, and I'll go back to my writing. So under alkaline conditions, what you're going to be doing is you're going to actually be deprotonating that hydrogen here. So that's going to disappear, that hydrogen, and you're going to form a delta negative charge, a full negative charge on your oxygen there. Okay. What that's going to now do is that's going to allow for a ion dipole interaction to actually occur here. Alright. Now an ion dipole interaction is much stronger than a secondary hydrogen bond. So the strength of the bonds goes secondary bonds, ion dipole, and then primary your strongest. So because you've actually increased the strength of the bond here, if we go back to the question, alright, explain why interactions are strengthened. Because you've deprotonated that carboxylic acid, you now get an ion dipole bond forming that is stronger, so the interactions are strengthened. Alright, structural formula of two polyamines, putrescine and spermine, are shown below. Okay, state the systematic name of putrescine. Each of those dots there, 1, 2, 3, 4, or kinks in the line, is a carbon atom, so it's 4 carbon atoms, right, which is butane. Butane. There's 2 amine groups, so it's diamine, and they're on the first and the fourth carbon, so it's butane 1,4-diamine. On the structural formula, circle a secondary amino group. So these two on the end are primary groups. This one and this one are both secondary. Notice that you don't go through any of the kinks in the line. You have to be very careful and clear with your circling, otherwise they will deduct a mark. And finally, amphetamine here asks you to do a structural form of the product by reaction of amphetamine with an acid solution. Well, here you've got an amine, which is a base. It can accept a proton, so you'd have you just write NH3 with a plus on it. The other way you can do it, if you want to, is you draw out the full structure, and down here to your nitrogen, you show hydrogen, hydrogen, hydrogen like that, so you can draw it out. The key thing is that you put the plus, okay, on your nitrogen. All right, really important. That's where you put the plus sign. Don't put it on a hydrogen. Don't write NH3 plus or anything, because that would be wrong. All right, I know this is a bit longer than I probably like to go for a video to go through, but hopefully it's helped clear up any misunderstandings. As always, if you've got any questions, just ask. I encourage you to go maybe back through it, try it on your own, and see how you go. Thanks, guys.